Hey YouTube, this is Mike, and in this video I'm going to be expanding upon a video I already did on how to code video poker in C++, in particular how to evaluate the odds of a pay table by speeding it up. You may recall that the program that I did in part 1 took 13.7 hours to run through all 2,598,960 possible starting hands. This video is going to speed that up by about 95%, getting the running time down to about 43 minutes. And it's going to do that by not evaluating all approximate 2.6 million starting hands, but only 134,459 of them. And because that is the number of different types of starting hands the player may get, and it's going to weight each one according to how many other similar ways the player can get that same hand. And this will all become more clear as we go. So I already pulled up the program that I developed in part 1. So here's the function deal, and what I'm going to do is first I'm just going to comment out everything, most of everything we just did, and I'll get rid of it later. I may just want to look at it for now. And what I'm going to do first is I'm only going to consider the hands where the player gets a 4 of a kind on the deal. And let's call R1 the rank of that 4 of a kind, which can be anything from 0 to 12. Recall how that we start numbering everything at 0, like good programmers do. And then the rank of the singleton can also be anything from 0 to 12, as long as it's not the same thing as R1. So let's check to make sure that they're different. And let's declare R1 and R2. So once we get this far, what are we going to do? At this point, we have decided what our ranks are. So eventually we're going to call the draw function. Now you may recall, in fact, let's look at it. Here's the draw function. See how this takes in 5 numbers that range from 0 to 51 according to the position in the deck of where the cards are that the player got on the deal. So we're going to need to convert ranks and suits to positions. So let's create a function called pre-draw that will do that. And that's going to take in 5 ranks and 5 suits and convert them to positions. So for the ranks, let's pass it rank 1 4 times. Once for each of the 4 times the player gets that rank on the the deal. And then rank 2 once. And then let's pass it 5 different suits. So for the 4 of a kind, the player is going to get 1 of each suit, and then for the singleton, he can get any one of the 4 suits. It doesn't matter. So let's just say that the suit is of the singleton suit 0. And then we're going to pass it a weighting factor, and that weighting factor in this case should be 4, because that singleton can be any one of 4 suits. So next let's make this function called pre-draw, and that's going to take into it, to avoid confusion, let's label the 4 ranks rank 1, rank 2, rank 3, rank 4, and rank 5, and then suit 1, suit 2, suit 3, suit 4, and suit 5. And we will also pass it that weighting factor, which we'll just call weight. And yes, I know, and so before I forget, let's have draw take in that weighting factor. And then down here at the bottom where it adds to total combinations, the number of ways the player could get any given hand of the draw, we're going to multiply everything by that weighting factor. And before I forget, let's go to the top and add weight to the things that get passed to the pre-draw function. And I forgot to say that this is an integer as well. I like to deal with integers wherever I can. Now draw, I believe I said this before, but draw takes in 5 positions from 0 to 51. So we need to convert these ranks and suits to positions. So let's just keep those terms the same, C1 to C5. So C1 is going to be rank 1 times 4 plus suit 1. And you may need to review part 1 in this series to know why I'm doing this, but recall how the ranks range from 0 to 12 and the suits 0 to 3. So by multiplying the rank by 4, that's going to make the position anywhere starting at 0 if the suit is 0. So C1 could be as low as 0, and if rank is 12 and say that the suit is 3, that would be a position of 51. So that is going to match the positions according to the way I set up the deck in part 1 of this series. And let's do the same thing for all 5 positions. All right, so let's go back up here to deal. And I think that we're ready to compile this. So let's compile it. And it says that I did not declare I, and it's right. You may recall that I commented that out. So let's add I here. And I got a warning about the printf function, but let's see if it works anyway. Oh, and it's telling me I forgot to declare pre-draw. That's absolutely right. So let's do that. We'll put it right before draw. And let's try again. And it succeeded, so let's run the thing. Okay, silly me. I forgot to actually call draw from pre-draw. So we pass it, C1, C2, C3, C4, C5, and the weight. And you may recall previously that setup told us how often it saw each hand when it was setting up the array of the score of all hands. I am going to comment that out. So let's compile this again. And it's telling me I made a mistake Yes, I forgot to, I put C5 twice. This should be C4. Okay, it compiled, so let's run the thing. Okay, I like these results. It's saying that on the draw, it saw a lot of different 4 of a kinds. And as it should be, if the player gets a 4 of a kind on the deal, he is always going to get a 4 of a kind on the draw, assuming he holds it. And it doesn't make any difference whether or not he keeps the singleton or throws it away. He's going to end up with a 4 of a kind on the draw. But one thing I'd like to do is I'm going to keep a count of the total weight that the program encounters, and I'm going to make it a global variable. I don't have to, but it's just going to be one less thing to keep passing around. So I'm going to call it the total weight. And I'm going to start it at 0. And then down here in, I'll do it in pre-draw. And I'm going to add to it that weight. And then here, let's print out the total weight. So let's make sure that it's running through the right number of 4 of a kinds. So compiling and running. So you can see that the total weight is 624. And this is right, and let me prove it to you. There are 13 possible ranks that the player can get for his 4 of a kind, and then once that is established, there's 48 possible cards the player can get for the singleton. So 13 times 48 is 624, and you see how the total weight is 624. So I'm satisfied the program is at least working for getting a 4 of a kind on the deal. Okay, next let's work on the full houses that the player may get on the deal. So it's going to be rather similar code to what we just did for the 4 of a kind, so I'm going to copy and paste. And let's make a comment for the full house. And here, for the ranks, we're going to pass it, shall we say, rank 1 3 times and rank 2 twice. And then for the suits, there are 2 different ways the suits could play out. Let's say that R1 is going to represent the rank of the 3 of a kind, so we will say that those ranks, those suits are 0, 1, and 2. And one way the suits of the pair could play out is any 2 suits that were already seen in the 3 of a kind. For example, 0 and 1. Now it's going to be real important that we get the weighting factors correct. So, what should be the weighting factor for this situation? There are 4 ways we could choose 3 suits out of 4 for the 3 of a kind. Then once we've done that, say those suits are 0, 1, and 2, there are 3 ways we could pick 2 of them for the suits of the pair. So the weighting factor is going to be 4 times 3, which is 12. However, what if the suits of the pair include the suit that was not seen in the three of a kind. So again, let's change the second suit to 3, because suit C was 3 was not seen in the three of a kind. So there's still 4 ways to choose 4 suits, 3 suits out of 4 for the three of a kind. And then there are 3 ways to pick one of them for one of the suits in the pair, and then the other suit is going to be automatically the one that's left. So the weighting factor is still going to be 4 times 3, which is 12. So we're calling pre-draw twice for the 2 different ways we can distribute the suits according to any given type of full house with regard to what the ranks are. And to help me look at just the full houses, I'm going to comment out the 4 of a kind code for now. So let's compile. And it compiled, and let's run it. So you can see that on the draw, the player is always getting a full house, which goes to show that in jacks or better, no matter what the full house is, you keep the whole thing. Now in some games like Double Double Bonus, this is not the case, where there's big incentives for getting 4 aces, but in jacks or better, there is no such incentive. And let's take a look at this total weight here, 3,744. How many ways are there to get a full house on the deal? Well, that the three of a kind can be any of 13 ranks. Then there are 12 left for the pair. And then there are 4 ways we can get the suits for the three of a kind, and 6 ways we can get the suits for the pair, because there are 6 ways to choose 4 suits, 2 suits out of 4. So 13 times 12 times 4 times 6 is 3,744. And yes, that checks out. So this looks right so far. Next, let's move on to the three of a kinds. So I'm going to copy and paste the full house code to save some time. So with the three of a kinds, there's going to be 3 different ranks involved. So let's add an R3 as a variable. In fact, I see that I already did. And so let's make another loop for R3. We'll say for R3 equals R2 plus 1, going up to 12 and adding 1 at a time. And let's have R2 go as high as 11. So this way, between R2 and R3, they will cover every way to choose 2 ranks out of 13. And let's make sure that neither one of them equals R1. So R1 is still going to be the rank of the three of a kind, and R2 and R3 will be the ranks of the 2 singletons. So in sending the ranks to pre-draw, we're going to go rank 1, rank 1, rank 2, rank 3, and then rank 2, and then rank 3. And we will say that the suits for the three of a kind are 0, 1, and 2, as was the case with the full house. And first, let's examine the case where the 2 suits in the three of a kind are the same, and one of the 3 suits represented in the three of a kind. So there are 4 ways to choose 3 suits out of 4 for the 3 of a kind, and 3 ways to choose one of them for the 2 singletons. So that weighting is going to be 12. And now let's consider the situation where the 2 suits of the singletons are the same, but this time it will be the suit that is not seen in the 3 of a kind. So again, there's 4 ways to pick 3 suits out of 4 for the 3 of a kind, and there's only 1 suit left over for the 2 singletons, so 4 times 1 is 1. So weighting of 4 there. Okay, next, let's consider the situation where both suits of the singletons are different, but they're both within the 3 suits of the 3 of a kind. So again, there's 4 ways to choose the suits for the 3 of a kind, 3 ways to choose one of them for the first for the first singleton, and 2 ways to choose one of them for the second singleton. So 4 times 3 times 2 is 24. Okay, next let's consider the situation where one of the suits of the singletons is within the 3 of a kind, and the other one is not. In other words, suit 3. So the number of combinations there is going to be 4 times 3, or back to 12. And now we're going to do the same thing, but this time we will make the first singleton have the suit that's not seen in the 3 of a kind, and the second one will have a suit that was. And that weighting is also going to be 4 times 3, or 12. So I believe that is all the ways we can arrange the suits in the 3 of a kind. So now let's, I'm going to comment out the full house code to just focus on the 3 of a kind. So let's compile this. And it worked. And now let's run it. So 85 seconds later, here are the results. We can see that on the draw, the player got this many 4 of a kinds, this many full houses, and this many 3 of a kinds. So this looks reasonable to me. If the player keeps a 3 of a kind, discarding 2 singletons, or if that's what he gets, he's always going to keep the 3 of a kind. That supersedes 3 to a royal or any other viable play. And if he keeps the 3 of a kind, that might improve to a full house or a 4 of a kind, or just stay at a 3 of a kind. You can see here this took 85 seconds. I did pause the video during that time. And how many total, what's the total weight of all those 3 of a kinds? You can see it says 54,912. So let's check that. There are 13 ways to get the rank of the 3 of a kind, and then there are 12 choose 2 ways, which is 66 ways to choose 2 ranks out of the 12 that are left. So that makes 858 ways to choose just the ranks. Then there's 1 missing rank for the 3 of a kind, and so there's 4 possible missing ranks for the 3 of a kind, and then 4 possible ranks for the 2 singletons. So there are 4 times 4 times 4, which is 64 ways we can arrange the suits. So multiply 858 by 64, and we get 54,912. So far, things are looking correct. Hey YouTube, so I have an embarrassing confession to make. After the 3 of a kind section, I believe, I took out the microphone. And so I made all these long videos for the 2 pair, the 1 pair, and the 5 singleton sections, and it was not recording a darn thing. But it was very long and tedious, so maybe it was all for the best. And so I'm just going to show you the code that I wrote in these silent videos. And I'm going to just leave it up to you to read them on your own time, and I think you'll be able to follow what I did. It's very much the same kind of logic as in the parts of this video that I already did. And I am going to leave a link in the video description to where you can get this code. And so here it is. I break it down by 3 of a kinds, 2 pairs, 1 pairs, and 5 singletons, and all the various ways you can distribute the suits. And I ran it, and this is what the results looked like. These numbers right here are the number of ways you get every hand on the draw, assuming you always play the way that results in the highest expected value. And these are the probabilities in return based on these numbers, and you can see that if you take the sum of the returns, you get 99.5439%. That is the expected return of 9-6 jacks or better. So the whole thing took 2,601 seconds. That's about 43 minutes and 20 seconds. So a significant reduction in time over, I believe, the 13 hours and 40 minutes from the first video. So in part 3 of this series, I'm going to show you how to cut down the running time from where we're at now down to about 2 seconds. And it's going to involve not looping through on the draw at all. So thanks for watching this video. I hope it wasn't too boring and that you learned something, and I will see you in another video. Bye.